Okay, so the polarization is very important feature for polarizing microscope because we are using their characteristic features to identification of minerals. So identification of minerals means we are using their optical properties. As I said last time, these optical properties all depend on this polarization effect, right? The cutting of polarized light along all the other directions except for one direction, which is characteristic for that particular polarizer. Okay, that particular polarizer contains, I mean, it is made so that it can vibrate only one direction. So that direction preserves there, and that light comes as a reduced intensity, having a reduced intensity to your eye, right? So if it penetrates through the minerals, depending on their crystal properties, you will see different features. So that's what we are interested in a petrographic microscope, because under the naked eye, we don't see such different characteristics when the light passes through minerals. So that is very important for our context. Okay, just a minute. Slides are not moving. Okay. Okay. Now, what happens when the light reaches your eyes? Right? So you can see, as I explained before, only one direction vibration is there, but no matter, it reaches to your eye. So that means you should be able to see some bright feature based on your sample, right? If your sample is having some different minerals or whatever it is, you can see because some of the light is coming. It's not total dark, right? If you can cut this vibration direction also, what will happen? Here it will be dark, right? Nothing will reach your eye. So that means you can't see anything. So in this case, you can see the light is coming. So therefore, something you should see. So that particular property you see, we call the property under PPL, right? So if we have another polarizer here inserted, right? Because you saw there is another polarizer in the microscope. We call it upper polarizer, right? So far what we had was only the lower polarizer. So you can see the light. But if you enter the upper polarizer, right? And remember, this upper polarizer is located or fixed so that it is perpendicular to the lower polarizer. So that means you have the upper polarizer fixed like, sorry, the lower polarizer fixed like this. Then your upper polarizer is fixed perpendicular to this one, right? So in that case, what will happen? Let's see, right? So there, it's fixed on opposite direction means here you see these lines, these broken lines are extending from west to east. So I said it's vibration direction. We call this line direction is as the vibration direction. So that's why you can observe uh, only the light coming parallel to that vibration direction, right? Because it's the vibrating direction of that particular polarizer. So if you have another polarizer fixed in opposite way means it should have vibration direction along the other direction, right? Perpendicular direction. That means north-south direction, right? So the first polarizer has vibration direction west-east, and the second one fixed in a perpendicular direction means we should have the vibration direction north south direction, perpendicular to the first polarizer. So then what will happen? Okay, so you have fixed the second polarizer, its vibration direction is north south, but now the light coming from the first polarizer is vibrating along east west. So what happens? Can this second polarizer allow this light to pass through? No. If light comes vibrating north south direction only, it can pass through because its vibration direction is north south now, right? Here the light is okay, from the first source, the light is coming from everywhere, all the directions vibrating, but it is filtered out by the first polarizer. Only the east west vibration direction light can pass through because the first polarizer has the east west vibration direction, but now it enters to another polarizer which has vibration direction north south, but the light coming through in this situation is east west vibration, so that it can't penetrate through. So what happens to your eye? There will be no light, right? Here you had light, here you had light, so you could see something. But when you insert the second polarizer, because I said this is a kind of an accessory, right? Optional plate, optional component. If you want, only you can put it in to the light ray path, right? If you don't want, you can remove it, right? It's a device like that. There's a small knob like thing. You can push it, or you can push it out, push it in or push it out, right? But this first polarizer is fixed without I mean, you can't change it. It's always there as a permanent component. But this one you can put in or put out, right? So now it's put out, it's not there, right? But if you put in, if you insert it in, what happens? Vibration direction is opposite, so there will be no light coming, right? So there will be total black, you don't see anything. uh, it will be black, right? So why is that? It's because the light coming through the first polarizer is in a direction along which the second polarizer cannot penetrate the light, right? Because its polarization direction is opposite, right? In case if you can send some light uh, along this direction, right, north south direction, then that light will come and bright, there will be some brightness to see from the object. Okay, so at this situation it will be black. So that's the function of the second polarizer, but we use it uh, as a kind of a optional component. That means when we need, only we insert it, right? By default it is not there inserted, but if you need, you can insert and see, because when we insert the second polarizer, also some features can be changed of the minerals. For example, this one being black is also important, right? For some minerals, if they become black, then that is also a characteristic feature for mineral identification, right? But remember, inserting this or not is the uh, another configuration. That means we change the configuration by inserting the light. So in that case, we call it cross polarization, right? The normal polarization is plane polarization. Here we said PPL, plane polarized light. Now what is coming is plane polarized light. But if we insert another polarizer here, the second polarizer here, we call it cross polarization. Cross polarization. So in that case, if in any case, if there is light coming along here, then we call that light as cross polarized light. But in this situation, in this particular situation, there will be no light, right? So but if you had a very slightly changed direction here, right, instead of east west, if you had a very slightly changed direction in a small angle due to some reason, right, you will understand it later. If you can pass some light slightly slanted, right, to this direction, then there will be light going through, because it is not perpendicular to this direction. There will be some light which can be resolved along this direction. Okay, so then the light, if any light passes through this one, then we call it plane polarized, cross polarized light, because it's after the second polarizer, right? So this is something like people use resolve I mean what do you call resolved components. Do you understand that? For example, if you have a ray or wave like this, right, passing through this, we have directions, uh, two perpendicular directions, like this. Okay, two perpendicular directions. If you want to resolve this light into these two directions, right? So say this is east west. You consider this as east west, and maybe down you have west, right? And in that case, this direction should be north south. Okay, north south. So I am now just reminding you some science, right? So if you have a wave here, just a minute. So if you have a wave here, what happens? Say this is P. You take it P, and you have an angle here. Let's say theta, right? You know theta. I can't draw it correctly. Anyway, so if you want to have a component of this P wave along this north-south direction, how do you do that? Has anyone can anyone remember your O levels? Not O level, A levels, physics or something. Is there anyone who can tell me the component of this P along this direction, north-south direction?
P cos theta.
That's right. P cos theta. Okay, cosine. Right. It's difficult for me to write here. P cos theta. Okay. So that means there will be some component along this direction. Okay. And similarly, there will be another component along this direction also, that we call P sine theta, right? P sine theta. So that means in any case, if you can slant, if you can slant this particular uh, vibration direction, then there will be some kind of a component like P cos theta or P sine theta to pass through this second polarizer. So in that case, you will see some sort of light moving along this direction as well. Otherwise, everything, I mean, for 90 degree, if this theta becomes 90, that means it's straight east west, right? If this theta becomes 90 means P should be along this direction. It's 90 degrees, right? East west direction. So in that case, there will be no component P cos theta or P sine theta. P sine theta means everything along the east west direction, right? There will be no component, so therefore it will be total black, right? So that's the theory behind this one. So if the uh, total vibration of this light passing through the first polarizer is east west, then there will be no component to pass through the second polarizer. But there is possibility for you to have some component through other directions except for the east west direction, just because of the mineral properties, right? If you put a mineral in between these two, right? If you put a mineral in between these two, that means somewhere here, if you put some mineral here, around here, right? If you put a mineral sample here, the light, if in any case, if this light which is coming along this direction, vibrating in this east west direction, can bend this light, right, to some direction like this, if there is any possibility for bending this light by this mineral, right? So in that case, the light will go slightly slanted after the mineral sample, right? In that case, it will be not east west, some other direction. Therefore, some light can pass through here, so that you will see some light here instead of black. Okay, that possibility is there because we put the sample here, right? We put the sample on the stage. The stage means between the first polarizer and the second polarizer, remember, here, right? So if you put some sample here, and if it, that particular sample, because of its crystal properties, can bend the light, the exerted light, then the second polarizer also can have some component passing through, so that instead of black, it can become bright, right? So that's why we use the second polarizer also, to see some sort of light under certain conditions. Okay, so this is how we consider this polarization is effective when we have another polarizer, right? More effective than the first situation, first configuration. That's very, very important. Okay, so we will see all these situations later on with examples, so that you can understand clearly. Okay, so before going further, is there any question? Please let me know if you didn't understand or something. As long as there is no sample here, you will see black, right? But if you put some sample here, and some minerals based on their crystal properties can bend the light, I mean, they can change the vibration direction, right? The penetrated direction can be changed. So in that case, there will be no more light, I mean, there will be extra component which is vibrating along other directions than east west direction. So that means that light can be passed through, because this polarizer has a characteristic way for propagation along the north south direction. So if the mineral can make the light in a slanted direction like this, so there will be always a p cos theta component to pass through the north south direction. So that's why that light comes to can penetrate through this second polarizer. Okay, so that component is very important. So you always have to think of the resolution of these light waves, or resolved component. We call components, right? In north south direction, you have one component called p cos theta. In northeast direction, in east west direction, you have a component in p sine theta. So p cos theta plus p sine theta will be composing the resultant light. That is what we refer here as p. Okay, so this is how uh, light passes through the second polarizer. If you can bend the light in between these two polarizers, otherwise it will not uh, bring you any light. Any question? Okay, this is important, right? So keep this in your mind. Otherwise, it will be sometimes difficult to understand some other facts in the coming slides. Okay, so there is no point of having light to, I mean, prevent it coming to the eye, right? To design a microscope. No, that's I mean, it's a technique used here, right? So that's the technique I explained. We can have an optional component as the upper polar, so that we can have light also coming through the second polarizer also, because once we put a sample inside, it will have a some bent vibration. So that's why. Okay. Okay. Right now, again, you can see when a thin section is inserted in between. So what is thin section? Thin section is the sample. Okay, thin section is the sample we insert in between the two polarizers. Okay, let's see how it will change. This is a thin section. So thin section means it's a glass slide. Okay, that's what we use as the sample, because I said you have to cut the sample, rock sample or the mineral sample into a very, very tiny piece and polish it until it reaches 30 microns thickness. Otherwise, the light will not properly propagate through that. So here you have the thin section. That's why we call it thin section, because it's very, very thin, right? 30 microns means very thin. So once you have that, the light passes through that, and you have various minerals in it, right? It's a rock piece, so you have a lot of minerals there. So each and every mineral has its own characteristic of vibration, the change in the vibrations. So once it passes through, the light again starts bending, right? That's what I explained in the previous slide. When you have a sample in between, the light vibration direction can be changed. So now it can have various vibration directions based on different mineral properties, so that there will be no longer polarization there, right? Because light vibrates in various directions, because this vibrated this polarized light will be bent and give you different vibration directions, when it passes through after the sample, right? So now after the sample means here, after the sample here, the light passes through this objective, right? This objective, you are looking from here, so your objective is aimed at your sample. So after the sample, the light comes like this, and this light will enter the second polarizer here, the second polarizer. So it allows the light to pass through only the north-south direction vibration lights, right? Because its polarization direction is north-south, which is opposite to the first polarizer, perpendicular to the first polarizer. It's east-west, here north-south. So previously it allowed only north-south light to pass, but now the light is bent again because of this sample. Now the kind of another a new set of light is passing through, but that light will be vibrating along the north-south direction, right? That light passes through, and you will see some colors because of the light is reaching your eye. Okay, some colors can be seen rather than being black, right? If no light is coming, then it will be black, total black. But now you can see some colors because of light is coming here, right? Some components, p cos theta component is coming, right? That's why you can see some light there, right? So some different colors are because of different minerals. Okay, because they don't have similar characteristics. So this is the characteristic we have to use to identification of minerals. So you can see different colors there uh, for minerals. So that feature can be used to identification of minerals. Okay, but one important, very important point is here. These colors shown here are not the actual colors of the mineral. So therefore, whatever the color you see here, you can see here green, yellow, orange, purple, black, all these colors are visible here. Vivid colors are here, right? But remember, these colors are not the natural colors of the mineral. So if somebody asks, is that this yes yellow color is the that particular mineral color? You have to say no. That is not the color of that particular mineral. Why? Because color of that mineral is determined here. Okay, so if you can see this light from if your eye is here in between before the second polarizer, you have to remove the second polarizer to see the real colors of the mineral. Because when the light reaches the second polarizer, it always distorts. So what you see here is a distorted color, right? So you have to remove this upper polar to see the actual color of the mineral. So actual color of the mineral is visible only after the first polarizer. After the first polarizer, then it reaches the mineral, and then through the objective, and you see under the eyepiece. That is the color of the mineral. So you only see the real color of the mineral at this point only. Okay, so remember that. Always you should see the actual color of the mineral here. When you observe here, only the actual color is seen. But uh, this color is not the real color of the mineral. This is a distorted color, but that distorted color is also characteristic for different minerals. Therefore it's important for you to note that distorted color as well, right? But if you want to see the real color of the mineral, then you have to remove this polarizer and see directly uh, after the first polarizer only. Okay, right. So anyway, we will learn about the uses of these colors as well later on. Right. So what is the conclusion then? Conclusion is that the minerals somehow reorient the planes in which light is vibrating. Do you understand that? Here, you have plane polarized light here, and once it reaches the mineral, that particular polarization direction is now reoriented. That means it's bent, like it's changed the orientation, right? So that is a particular special property of each and every mineral. It can reorient the light. So that reorientation also helps us to identify different properties, right? Not the color property. Yeah, of course, color property is identified here, but when it reaches another polarizer, then that reoriented light gives you some different colors, which is not the natural color of the mineral, but that different colors are also important for us to identify the minerals. So anyway, the conclusion should be the minerals can reorient the planes of light of vibration, so that that can also be used as a characteristic feature to identify minerals later on using the polarization microscope. So that means some light can pass through the upper polarizer. Some light can pass through the upper polarizer because, as you noted before, only the P cos theta component can be passed through the upper polarizer. Right? That's why we call it some light can be passed, not all the light, right? Because there is another component coming through east-west direction as well. But east-west direction is not allowed to pass through this second polarizer, only north-south direction. So that's why we call it some light can be passed through, some component only. Okay, right. So that's why you see here some vivid colors, but these vivid colors are not the natural colors of the mineral. So if suppose this is say quartz, this one, I'm just giving an example. But the color of quartz is not reflected correctly here, right? If this is pyroxene, this green color is not the real pyroxene color. Okay, so that's a different color. It's a distorted color actually, uh, because this is after the second polarizer. That means these colors are seen under cross polarized configuration. So therefore, we call this configuration as CPL, cross-polarized light. So if you observe the mineral under CPL, then you will see these vivid colors. But if you observe the mineral under PPL, then you see some different colors, but not vivid colors like this, right? Less strong colors. You can see the natural colors you can see. So PPL here under plane polarized light. Under CPL, it's here, right? This observation is CPL and this observation is PPL. Okay. So this is a very, very fundamental feature of a polarizing microscope, and which is here as vibrating. All the directions are coming under vibration direction because of vibration directions and changing of vibration directions after the second polarizer. Okay, even here, right? You can see some grains stay dark, right? So stay dark means they do not pass the light after the second polarizer. right? Black means there is no light coming after. So the black ones here, you see here black minerals, that means they cannot reorient the light. Only the minerals which could be able to reorient the light can pass through here, right? Right. If something cannot be reoriented, that means always north, always east-west orientation only. So if any mineral is there here, which cannot reorient the light, their vibrate the passing ray will be along the east-west direction. So east-west direction, when it reaches the second polarizer, what happens? It's totally cut. It cannot go through that because its vibration direction is north-south. So such minerals will remain dark in this second configuration. Under the CPL, those minerals will be remain dark, right? Only the ones who could reorient the light into other directions can pass through and give you a vivid color, right? So that's also important. Some grains stay dark, so that is also an important feature for that particular mineral to identify. So if some mineral remains dark after you insert the second polarizer, that is also an optical property of that particular mineral, which we can use that particular property to identify that mineral from, distinguish that mineral from other minerals, because other minerals can pass light, but this mineral cannot pass light under the CPL. So that means it's a characteristic feature to distinguish it from uh, other set of minerals, right? So we will see what kind of minerals can remain dark under the CPL. That is also an important feature for mineral identification. So this is the essence of polarizing microscope. We can use the optical properties differently to identify minerals. So this is very, very useful rather than observing minerals under cross polarized under unpolarized light, right? So if you just look the hand specimen, that means unpolarized light, right? Normal light, under the normal light, if you have a mineral with your naked eye, observation means unpolarized light, right? But if you can put that mineral into a polarization device, then you can observe them under polarization, whether it is PPL, plane polarized, or cross polarized. Then you can distinguish different colors, different properties, sorry, different properties of minerals. That's the use of polarization microscope. Okay, so this reorientation is very important factor, as we now understood. So we have to really recognize what kind of reorientation uh, can be considered. And also, as you know, the stage of the microscope here, we told that the main two features of my polarizing microscope is having a polarizer plus having a rotatable stage. Why do we have a rotatable stage? Because in a normal microscope or biological microscope, there is no rotatable stage. It's just a fixed stage. You can't rotate it. But for us, for identification of minerals, we need a rotatable microscope, because a rotatable stage, because that also gives you some optical properties, important optical properties. So that's why we need a rotatable stage. So when you rotate the stage, what happens? Actually, most of the minerals give a change to its color when we rotate the stage. That is also important factor. Okay, so if all the observations that we have already made are under fixed stage without rotating, but while you observe the sample, you can rotate the stage also. Then you will see the colors you observed here will change. Even under PPL or CPL, no matter, the colors can change while you rotate the stage. That means, for example, this is one stage, one situation, this greenish color. But if you rotate the stage just while you see this greenish color, it might change into this color, this purple color. When you change, this purple will change into green color when you rotate the stage. So likewise, right? When you rotate the stage, that can happen. And also, sometimes this type of dark minerals can change into uh, some grayish appearance like this, right? So in that case, uh, there is light passing through, right? But even when you rotate the stage, if this mineral become dark, keep dark, as remains dark as it is, then that's a characteristic feature. But if you rotate the stage and if this dark changes to gray or some other color, then that is another feature, right? So that is also important. So keep in mind that in that case, that light, it's not a property of particular reorientation. That means it is also a property of changing color, like here, vivid color, right? So some minerals can remain dark, means those minerals cannot reorient the light at all, right? Some minerals can remain dark, but when you rotate the stage, become bright, means they can still reorient the some component. That is also another factor. If the mineral remains dark all the time when you rotate, even when you rotate the stage, that means those minerals can not reorient the light at all. Okay, this reorientation cannot happen for some minerals at all, but some minerals can reorient the light when you rotate the stage. That means when you change the mineral angle, rotating means that, right, you are changing the angle of mineral, right? It's orientation. So that can uh, allow pass through some light in a different direction. So that is another feature, right? So likewise, very complex features are there related to the polarization light. So you can observe all these things when you come here for practical sessions, and there you can really understand what these features we are talking about. So therefore, keep in mind all these features, all these properties, and all these principles, so that you can understand in practical lessons very clearly. Okay, so we'll see here, most mineral grains change color as the stage is rotated. Okay, these grains go black 4 times in 360-degree rotation, exactly every 90 degrees. So when you rotate the stage 90 degrees, some minerals become black, but if you rotate another 90-degree, in between it will become bright, but again at 180 it will become black. Again it will bright black, like that. 4 times can be black when you rotate the stages. But some minerals remain dark even when you rotate 360 degrees. As I said before, they never change, they never reorient the light. So that is a very, very characteristic property of that particular mineral. If it becomes or it remains dark every time under the CPL, cross polarized light. But under the CPL, uh, these minerals can change their colors intermittently every 90 degree. That is also another property, right? Even under PPL, plane polarized light, also when you rotate the stage, these minerals can change their color. So under the PPL, I said they should exhibit the natural color, right? CPL, they exhibit a distorted color, but that is also useful. But the natural color is displayed under the PPL, plane polarized light. But when you rotate the stage also under the PPL, they can change the color, but that color is a kind of a change of strength of that particular color. If it is brown, if you see it brown, when you rotate the stage, it can go light brown, pale brown, like that, and become strong brown again change light brown, like that, right? It never become black, right? It never become black. That is another feature, right? So anyway, the use of the stage as rotatable is very useful because we need to have this rotatable feature to understand how these colors change. The way of changing the color is also an important factor for mineral identification, right? So we'll see some minerals can become dark, right, when you rotate the stage, right? Again, normal color, like that. So always there will be 90 degree to become dark. Okay, so this feature, so these minerals, when they become dark at 90-degree rotation and again become bright when you rotate further, again black, again bright, like that, alternatively, they change the color, are called anisotropic minerals. Okay, they are called anisotropic. The name or the group of that mineral is called anisotropic mineral group. Okay, so this is important. uh, but as I said before, if some minerals remain black all the time, if they remain black all the time in all orientations, right, those minerals are called isotropic minerals. Those minerals are called isotropic minerals. So always remains black, right, unlike the previous situation. These minerals are called isotropic minerals. So those the minerals which remain dark every time under the CPL, cross polarized light, right? CPL. Those minerals are called isotropic minerals. Okay, but sometimes most of the minerals remain like this, right? Bright and dark, bright and dark, right? Here some are dark here, but this dark may be the dark position of this particular mineral. We don't know, right? We have to see by rotating the stage. But some cases, maybe this mineral always black, right? In that case, it never allows light to reorient through the second polarizer, cross polarized light. So such minerals are called isotropic, but the other minerals are called anisotropic, right? So in a rock, you can have the group of minerals can be isotropic or anisotropic, right? So we will see this characteristic feature or this character, isotropicness or anisotropicness, can be used to distinguish minerals, right? Some minerals are isotropic, some minerals are anisotropic. This is important for mineral identification. Okay, so now basically, minerals can be divided optically into two groups. So this we call optical characterization, two broad categories: anisotropic minerals and isotropic minerals, right? So isotropic minerals will give you some color, although they are black in the cross polarized light. Always, they can give a color under the PPL, right? Under the plane polarized light, they can give a color, but under the cross polarization situation, they can remain dark, right? So see here, right? Here, if you have the thin section or the mineral here, all the minerals can give you some color under the PPL, plane polarized light, because some light, this plane polarized light, everything is coming out, but some minerals can only reorient the light, as I said. Those light reoriented light minerals will give you another color here, distorted color here. But those who cannot reorient the light, the minerals which are here, which cannot reorient the light, will remain uh, its vibration direction the same as west east direction, east west direction, so that that light cannot pass through the second polarizer, so that finally they will remain black every time. Although you rotated the stage, they will not change their color, right? Because they can't reorient. So under the PPL, that means sorry, under the PPL, all the colors will be all the minerals will exhibit some color, its natural color. But when you enter the second polarizer, they will display you vivid colors, because being able to reorient the light. But some minerals remain black, as I said. So such minerals cannot reorient the light. So the minerals which could reorient the light are called anisotropic minerals, as we clearly mentioned in the previous slide, because when you rotate the stage, they can change the color, right? But those minerals which cannot reorient the light will remain dark even under rotating the stage. Such minerals are isotropic minerals. So here in this image, if you see, like here in this case, those minerals which can change their own colors while rotating are anisotropic, and those who are remain dark all the orientations while you rotate the stage also, they are isotropic. So you have two isotropic and anisotropic properties of minerals. Okay, right. So this is a very, very important feature with respect to the polarizing microscope. Okay, so I think you can now understand the important properties of light, which we use under the polarizing microscope uh, to understand the mineral. So all these properties we call uh, optical properties, or uh, kind of photo properties of minerals. Optical properties or photo properties. We call photo properties also because photo means light related things. Okay. So please, just a reminder, please uh, put your name and your number to mark the attendance in chat box. Okay, so if you have any question up to this point, do you have any question?
So, like, are there any stones which could be appear as opaque? Like, once you take this thin slice,
Yes.
will there be any areas which would be opaque? I mean,
Yeah,
like it doesn't
that's
pass light.
yeah. I understand. Good point. Yes, I didn't explain it yet, but I will take since you asked the question. Now I will use that also. Just a minute. Okay. Now we have the sample here, thin section here, right? So we have number of minerals here, right? We have the plane polarized light coming, and it passes through minerals, and you can see some light is passing through. So light is passing through minerals means those minerals are able to penetrate the light, right? That means they have the transparent feature. So we call something transparent if the light can penetrate through it. But if the light cannot penetrate through, I am talking about the ppl situation, okay, not this after the second polarizer, because this is artificial blocking, right? Second polarizer is a kind of artificial blocking of light, right? It's not because of the mineral cannot penetrate the light. It's just because of the orientation direction only, right? If this uh, north south orientation is possible, then the light will pass through, right? So this explanation, the present now, what I am going to explain is under the ppl only, right? So if under the ppl condition, because you have only one polarizer there, they are still every mineral should be able to penetrate some part of its light uh, in one direction after plane polarization. So this light will go through the mineral and it can penetrate through, right? Those minerals are called transparent minerals, right? But even if some minerals can lie here in the sample, which cannot even pass through this light, even this plane polarized light, it cannot pass through this light. So such minerals are called, as you correctly said, opaque minerals. Okay, opaque minerals remain black under the plane polarized light also, right? All the other minerals will remain with some color because they can pass through light, but opaque minerals cannot pass through light at all, right? Even under plane polarized light, they cannot uh, pass through. That means they remain black, right? What are the opaque minerals? Some example, one or two opaque minerals, can you say?
Graphite.
Yes, graphite is one. What else? What else? So opaque means even you make it very, very tiny or very thin film, like 30 microns, right? Even that, even less than that thickness, the light cannot pass through. That means even if you put a torch you will see black, right? The light cannot pass through. But other minerals can pass through light. They are transparent. Graphite is one such mineral which is opaque. And what else?
Okay.
Sorry?
Okay.
Sorry, I didn't hear it clearly. What was that?
Malachite.
Malachite?
Yeah.
Malachite? Malachite. Malachite is copper hydroxide, isn't it? Well, malachite, yes, it can be. Yeah, it's a copper bearing ore mineral. Yeah, most ore minerals remain dark. Yes, it can be. Yes, I'm not sure because I'm not very much familiar with that malachite under the thin section. But since it's a ore mineral, it's an ore mineral, it can be. Yeah. What are the other one? Commonly, we can call ore minerals, all the ore minerals, right? ORE, ore minerals. Those remain dark. Those remain black under the plain polarized light. For example, ilmenite, titanite. Sorry, not titanite. Ilmenite. What else? Ilmenite. All the oxides. Yeah, hydroxide also. Yeah, you are correct. Malachite is also correct. Oxides, hydroxides, they remain dark, right? Oxides means, I mean, not all oxides, right? Don't get confused. All the ore mineral oxides, okay? For example, spinel is an oxide, right? But spinel is not dark, okay? Uh, Opaque minerals means ore minerals mainly, like magnetite, hematite, like minerals, they can remain dark, okay? They cannot penetrate light through them. So they are always dark under the ppl also, right? But other minerals which are transparent cannot remain dark under the ppl, but they can remain dark under cpl at a certain situation, like we explained uh, just a while ago. See, this darkness doesn't mean that they are opaque, right? It's just only one orientation only, right? Other times they become bright. But if you have always dark like this is opaque, right? But opaque doesn't mean all the isotopic minerals are opaque, right? Opaque means the definition opaque comes to the minerals which remain dark under ppl, plain polarized light, right? This situation is not plain polarized light. This is after the cross polarization, right? This is after cross polarization. So therefore, being dark under the cross polarization doesn't mean the mineral is opaque. Okay, if the mineral is dark all the time under the ppl, plain polarized light, then you can call that mineral an opaque mineral. All the other minerals are transparent minerals, and these transparent minerals can be divided into two groups: anisotropic minerals and isotropic minerals, right? Anisotropic minerals are minerals which have dark, which become dark at every 90-degree rotation only, right? Isotopic minerals are always dark when you rotate the stage under the cpl. So that's the difference. Is that clear?
Yes, sir, it's clear.
Okay,
Thank you, sir.
right. Right. Some important words for you to remember, vocabulary. That's also important because sometimes you get confused when you try to explain these properties. So please make sure that isometric minerals. Do you know isometric minerals? I think you have done some crystallography. Have you? Not yet. Crystallography. Have you done any crystallography?
Yes, sir, we have done.
Ah, okay. Right. Then you know isometric minerals, right? Those are
Yes.
called cubic minerals. Remember cubic system? So those are isometric system or cubic system. those minerals, for example, garnet is an example for that isometric system. They remain isotropic, right? Under CPL, when you rotate the stage, they keep dark always. It's a transparent mineral. That means garnet can penetrate light. So that means under PPL, you can see its color, very beautiful color, pinkish color is there under the PPL, plain polarized light. So under the microscope, the natural color of garnet is purple, right? We call purple, right? But when you rotate the stage, when you insert the second polarizer, or analyzer, we call the analyzer also for the second polarizer, then it becomes dark all the time. Not in every 90-degree become dark, always it's dark. Okay, so that is a characteristic feature for isometric minerals. So minerals which are belonging to the cubic system, they become dark in CPL, cross polarized light, when you rotate the stage. They cannot reorient the light. That's the reason, right? They cannot reorient the light, so that always they are dark under CPL. But PPL, they can be having a color because they are transparent, right? They are not opaque. So these minerals are always black in cross polars, CPL, cross polars. So what are the other some examples for such minerals? Can anyone tell me one example, another example for isometric minerals which remain dark in CPL?
Spinels?
That's right. Good. Spinel is again isometric and they remain dark in CPL. What else? Very not many minerals, only few.
Diamond?
Yeah. What else? That's correct. There is
Fluorite.
sorry.
Fluoride?
Yeah.
Fluoride.
Good. Yes, fluoride. That's what I expected also. Fluoride. Yeah. Those are the very common isometric minerals which remain dark in cross polars, right? There may be few more, but these are the most commonly found minerals in our rocks situations. Okay. Right. The second point is all other minerals except for these isotropic minerals are anisotropic, as I said. That means except for this isometric system or the cubic system, all other system minerals can be anisotropic. Okay, except for opaque minerals. Right? They are capable of reorienting the light. If they can penetrate the light when it is under PPL, that means when you insert the cross polars, you can have some colors, right? But while rotating the stage, at a certain point in every 90-degree may be dark, but not always. So therefore, you can term them as anisotropic. So isometric minerals or the cubic system minerals remain dark all the time, even under cross polars entered, so that they become isotropic group. Okay, so all the anisotropic minerals contain one or two special directions that do not reorient the light. So that is a new point that we haven't discussed. So we'll go back. Okay, so this mineral remain some color under cross polarization, but we said every 90 degrees it becomes black. So becomes black means there is no light passing through the second polarizer. That is the point you have to keep in mind, right? So that means although these minerals can reorient the light here, that's why you are getting a color here, reorientation, but still there are some direction, actually two directions, one or two directions are there for depending on mineral, which cannot reorient the light. For example, if you had a mineral here oriented in that particular direction, in that one or two direction, in that direction the light cannot reorient, so they will remain dark. That's why you are having this darkness in anisotropic minerals also when you rotate the stage. There is some disturbance outside, so I don't know whether you can hear me well. Right, so just keep in mind that there are some one or two directions depending on minerals, right? Anisotropic minerals. In anisotropic minerals, there is a direction. In some minerals only one direction, some minerals two directions, where this reorientation cannot happen, right? One or two directions. So these two directions, uh, if the light passes through particularly on these directions, then even those anisotropic minerals remain dark. Okay, that's why when you have a rotating stage, those minerals become dark in those 90-degree positions, right? That is those directions, the light orients in those directions. So these directions, if they have only one direction, one such direction, such minerals can be named as uniaxial mineral, because there is a special axis, orientation axis. And some minerals contains two such directions. So those special directions are called, such minerals are called biaxial minerals, right? So now remember, broadly, these transparent minerals, that means the minerals which can penetrate light, can be divided into two groups as isotropic minerals and anisotropic minerals. But now we know that anisotropic minerals can be further subdivided into two, that is uniaxial minerals and biaxial minerals. Okay, so the broad two categories are isotropic and anisotropic can be divided further into two, that is uniaxial and biaxial minerals. Okay, so these are the important points that you have to take home today, where these minerals uh, these minerals are divided based on their optical properties. We considered only optical properties, nothing other than that, right? Whether the light can pass through and how this light, the pass through light, behave. Those two were considered for categorization of these minerals. Therefore, we call optical categorization of these minerals, right? All these system categorization, for example, isometric system, orthorhombic, monoclinic like categorization are not based on light properties, right? They are based on their physical properties, right? Their crystal shapes, their orientation planes, like that, right? But now today we learned how the minerals can be categorized optically, right? Optically means based on the light, behavior of light through those minerals. So isotropic minerals and the anisotropic minerals, those are the two broad categories. And anisotropic minerals could be subdivided into two, that is uniaxial and biaxial. Actually, this uniaxial and biaxial definition comes when there are some special directions where along which the light cannot be reoriented. These are not physical axes like C axis, A axis, B axis, like we could name in minerals, right? I mean systems, crystal systems, right? Cubic system, orthorhombic system. There we take two axes in different angles, like that. Not like that, right? These are just some kind of hypothetical axis along which light cannot be reoriented. That's the only point. Okay, uniaxial and biaxial. So just keep in mind, these are the important vocabulary actually, because we always hear isotropic, anisotropic, uniaxial, biaxial, like that, right? So all of a sudden, when you hear such a term, you must be able to realize what sort of characteristic that we are talking about. Okay, so these are the important points for today, based on the light penetration through optical microscopes. Okay, so do you have any questions? Today I'm going to finish the lecture a little bit earlier, because I have another commitment. So if you have any question, you can just ask me now.
So do you get any mineral which is completely bright?
Completely bright.
Yes, once you rotate it, like those are like once you rotate it, like isotropic ones will be dark,
Yeah.
so anisotropic ones will be dark and bright. Do you get anything which is
Yeah.
completely bright?
Yes. That means yeah, we have
Polycrystalline materials,
sorry.
polycrystalline
Yeah,
materials.
yeah. Actually, there will be such situations. Even natural minerals will behave not 100% dark at a certain situation, right? So we call that's a special property called extinction. Also, there is some light passing through. Therefore, they will not extinct 100%, right? There are such minerals. So when you have practicals, you will see uh, such minerals which do not go full extinction, right? There are such minerals. Yes, such minerals and materials. Any other question? So the practicals are very important. So please don't miss the practicals, and also don't miss the lectures, because if you miss the lectures, it will be difficult for hard to I mean for you to self learn also, because you need some explanation as at this introductory level, right? But you are encouraged to refer the books when you come to the university, because at the science library there are very important books and very descriptive books, textbooks in the science library. So you have the access to the science library already. Therefore, please try to refer them as when you have some time, right? Any time if you visit the university, you can go to the library with your identity card and refer the mineralogy books. They are categorized under class number 550 in the shelves, right? Okay. Right. So we'll stop here for today then. We will continue with the next lesson next time. Okay. Thank you very much.
Thank you very much, sir.
Thank you, sir.